sounds good. So it's now getting time for your talk. So
Okay.
just sort of I'll mute myself.
Okay.
Yeah.
So shall we start?
Yeah.
Okay, I'm introducing you. So it's a pleasure to have Devavrat Shah here. So let's start with the most important distinction here. He is the alumnus of IIT Bombay, a gold medalist to boot, and also a distinguished young alumnus. Now he's a professor at MIT and heads the data science program. He has 7 honors. I would like to mention the Erlang Prize for Young Scholars, which is a very kind of non-trivial, sought-after kind of award. And there are several others, and things like the Best Paper Award, etc. He picks up, I guess, a couple every year. So no point trying to even attempt to list them. And he is not only working at the frontier of the field, but he often defines the frontier and has started many interesting problem formations and paradigms which others have followed upon. And this is his latest synthetic control applied to various, including COVID, he has applied to many things. So today we will tell us about synthetic interventions. Okay, over to you, Devavrat.
Right. Well, Vivek and Nikhil, thank you for the invitation. It's always a pleasure to be at IIT Bombay, whether physically or virtually. Of course, I'm hoping that I would be physically there soon. While that happens, this is a great opportunity for me to tell you a little bit about one of the topics, synthetic interventions. This is based on joint work with a few of the students at MIT. In particular, it's primarily thesis of Anish Agarwal and Dennis Shen. The synthetic intervention is a method that tries to do causal inference with observational studies. As we shall see, is also a nice way to bring together experimental studies and observational studies. Now, again, if you have not been to a talk with causal inference as I had at least a couple of years ago, all of these would sound Greek and Latin, and I will define all of them as I go through the talk. So to explain what this method does and what are these questions of causal inference, observational studies, etc., let's start with one of the timely examples of COVID-19. Now, what I'm going to present here is a simple case study, and that's how I would like you to view this. I wouldn't like you to view this as any concrete or strong decision. Okay, so I will tell you sort of what is the data. I will tell you what method does, and then based on that, you may make your conclusions. So with that in mind, here is a chart which plots time axis or days on x-axis and on y-axis number of deaths. The way we have defined zero is the day on which 80th death in the country, here United States, it was reported. Okay. And of course, as you may imagine, there was slow progression initially, and then after that, there was an exponential growth. Okay. Now, the question that one would like to ask in this setup is that United States as is went through a specific sets of policies and specific sets of intervention early on, and that led to this outcome. Question is that what would have happened if United States had gone through different policies potentially leading to different amount of human restrictions, different amount of mask wearing and whatnot, and that leading to different health outcomes. Question is that can we quantify that? Especially, can we quantify that on day zero, sitting here with the only data that we have seen till that point? Because I want to effectively forecast what would happen going forward under different policies. Now, the way we're going to sort of think of policies in this case study is simply mobility restriction, and we're going to look only for first 15 days. Okay. Now, mobility restriction is measured in this case study through the Google mobility data that was reported. And in particular, the way we would measure it is there was a normal times when there was some mobility compared to the normal time and the mobility, how much mobility has reduced or increased in percentage wise. Okay. And in particular, the mobility restriction at the transit stations and the retail places would matter the most. Now, of course, this is one country, United States, and since we have only one trajectory, it's really hard to decide what will happen. In an ideal world, what I would have liked to do is I would have liked, let's say, 3 United States at day 0. United States 1 would have very strict lockdown leading to a large amount of mobility restriction. United States 2 having maybe moderate mobility restriction, and United States 3 with, let's say, no mobility restriction. In effect, as you may know, in at least United States, in the first 15 days, there was not much that was done, and hence it was as if there was not mobility restriction at all. So it was United States 3 that was got realized, but if I could do 2 and 1, then I can actually do, I'm doing an experiment with randomized control, so to speak. But 1, 2, and 3, I compare their outcomes and then decide how would the different outcomes look like after day 0. Of course, as you can imagine, this is impossible because we only got one country. So the question is that how do we do counterfactual evaluation for United States, even though we have only one United States? This is exactly what one calls a question of causal inference with observational data. Okay. Let me pause here for a second and see if, just as I'm setting this up, any question that has come up, feel free to unmute yourself and ask question.
A quick question.
Yes.
What is your argument to choose 80th? I mean, just you like the number, or is there some other interpretation to the 80?
Thank you, Matt. Great question. So, reason we chose 80th death is because most countries reacted to policy after some deaths were reported. If we waited too much, let's say 10,000 deaths, it's too late because countries have already implemented some intervention. Okay. If we went too early, that is, let's say 0, effectively maybe so country has not started intervention, and then so we are looking at a time where countries are as if they were in the pre-intervention time. Okay, so 80 turns out to be, for the data analysis purposes, the right number. That's where, in some sense, most countries are aligning nicely.
So in some sense, you derived it out of the data, is it? The 80 was derived from the data that you had.
That is correct. So 80 was derived from the data. Okay. Absolutely. And it turns out to be the right place where just around that time, most countries go from no intervention to some intervention. Thank you. Any other question? Okay, so got 10 seconds online pause of question, which means no questions. All right, so just to see what has happened across the globe, what I'm doing is here, I'm plotting roughly 27 different countries, and then average mobility restriction at the key places, in particular, as I mentioned, transit and retail places. And as you can see, there's a nice clustering, right? There is green countries, which in first 15 days after 80th death saw a severe mobility restriction. The orange countries saw moderate restriction, and the blue country saw a low mobility restriction. Okay, and so these, in my mind, would be 3 different type of interventions that I want to see in the first 15 days after 80th death in each country. Okay, and of course, as you can see, India, as you experienced very severely in first 15 days after 80th death, they were in severe restriction. This was the These were countries such as Turkey and all that, and then United States and UK here. Okay. And again, so the question that we want to know is what happens to United States under each of these three restrictions and the trajectory of death. Okay. So what I will tell you in the remainder of the talk is a simple method that utilizes data for United States as well as all other country. In particular, for United States, it will use data only up to day 0. For other countries, it will utilize all the data, and using all the data for all other countries and United States up to day 0, it will try to produce counterfactuals, which are the green, the orange, and the blues. The green, the orange, and the blues are simply counterfactual produced on day 0, saying that what would happen to United States under 3 different interventions. And now this dark blue, I'm just recalling that this is actually what happened to United States. And now, as you can see from this, well, it looks like, at least visually, maybe the method is doing something right. And hopefully from this, you can sort of make all sorts of conclusions and decision. And one conclusion I would make is that maybe initially a moderate restriction, not severe, not no restriction, could have been a reasonable way to manage the country, the economy throughout everywhere. Okay, and seems commonsensical. Okay, just to sort of see how do other countries fare in the similar sense. Again, for UK, we use only data till the day 0, but for all other countries, we use data all over. And then using that, 3 counterfactuals are produced, same green, severe, orange, moderate, and the blue, no restriction. These are the 3 counterfactuals that come out. So now, UK and United States were countries where they actually experienced very low mobility restriction. We could ask the same question, what happens to the countries in other groups? Here are 2 examples for countries in the moderate group. This is Brazil and this is Turkey. And as you can see, of course, no method is perfect. There is some deviation that's happening. And then finally, the last two countries in the last group, which is India and Ireland, and at least in initial days, it was severe mobility restriction. So I think I got wrong labeling here, extremely high mobility restriction. And this is what happened. Okay, let me pause here for a second, see if there's any question.
Maybe later we are trying to do that. You are trying to somehow quantify this idea called restriction, is it? Maybe later you are going to do that. I mean, how do you quantify mobility restrictions?
Correct.
I mean, severe, lower.
Yeah. So let me just go here. So what we did is that the way we quantified it is as this. So using Google mobility data as an aggregate number across a country, there's a day 0. You look at sort of the time series of mobility, aggregate mobility across a country in terms of retail and transit places. And let's call that as a 0%, because that's a normal. After day 0, look at the time series, look at the average value there and average value here. Take that and look at those 2 numbers and see if it's less than 5% change above or below, then I would call low. If it's between 5 and 35, we'll call it moderate. And if it's greater than 35, which we'll call it severe.
Okay, yeah.
Thank you for asking that. I'm sorry I didn't specify that.
It's okay, but that's fine.
Devavrat, one question about the graphs that you just showed. So what particular features of a country kind of impact the varying trajectories? So for example, I mean, things look different for what the US and the UK are showing, right? Whereas
absolutely,
I mean, you're including kind of the data from a lot of other countries to kind of decide both for US and UK. So what about US and UK kind of makes the distinction in the trajectories? So for example, I mean, it looked like for the US, a moderate or low mobility, both are very close to each other, but that is not the case for UK. There is
Absolutely.
a bigger gap. So
Good. So, great question. Thank you. So, a quick answer now, and this actually is a perfect cue for me to go to the next few slides. The data that we're utilizing is for every country, we are utilizing only this kind of curve, nothing else. So this is all we're utilizing. That is, we take a country, we define a notion of day zero, we say what is, we plot this curve, we use this as a sort of a curve and this curve, and this is all we are utilizing.
I see. Okay.
So it's simply observational in that sense, and hence observational study.
Okay.
No features.
Okay.
So,
And the curve kind of starting from day zero onwards only uses for that particular country only uses the data till day zero, right?
absolutely.
Okay.
But from other countries, it's using data beyond day zero.
I see. Okay.
Great
Okay.
point.
All right. Thanks.
Thank you.
I have a question.
Yes, Pramod?
Yeah, so just was wondering if your model takes into account the differences in the social networks of different countries, the industrial nature and the average age and the demographics and so on.
So, short answer is no. At some level, actually having a clean way to include those things would definitely help a lot. And I think that's something that one should do. There are two challenges, as you will see. One is there's no clean, obvious way we know how to do it. So I think it's a nice algorithmic or / methodical question. As you go through the talk, hopefully it will become very clear. And the second is, I think having that information appropriately included might sort of help not only do, as you will see, this method is nice in terms of doing local counterfactual future, let's say local counterfactual analysis, not a global one. In a sense, what you want to do is that as we have experience, we have to sort of keep relearning the model, so to speak. And there are some of the successes we have not sort of put everything together, but this is where having additional information utilized in the model is very helpful. But short answer, for this case, we are not using.
Yeah, because it's not clear what the model is.
Good. So perfect question. How?
Okay, yeah, I will wait for the next slides. Thank you.
Excellent. Okay. So again, bottom line is it's a simple causal inference question. That is, how do we decide for a given unit all possible outcomes, even though you might observe just one? Okay. And we'll utilize so what I'm going to do is I'm going to utilize a classical framework of causal inference called potential outcomes. So originally proposed by Newman and then reproposed and popularized by Rubin in 70s. Basic idea is this, that every country has three different personas in this setup: a low persona, moderate persona, and high persona. Under each persona, we observe three different distributions. Okay, and the distribution can be indexed by, let's say, intervention D: low, moderate, or high. Okay, D star is something that we have observed. For example, in the United States, on days 0 to 15, we observed that D star was low. Okay, and of course, in that case, what would happen is that my observation would be what I really care about under D star. That is, average behavior under D star of me as a continental United States I observe a random variable of that such that in expectation, it's equal to this mean trajectory. What I really want to know is M sub D, where D is moderate and high, not just D star. And of course, for D star, I would like to denoise it from Y. Okay. So again, there are three different distributions: distribution that realizes under low restriction, moderate restriction, and high restriction. For each one of them, there is a mean trajectory that I really care about estimating because I observe noisy things. Okay. For each country, I'm only observing one of these three different noisy trajectory. And from there, I want to figure out exactly which of these three different trajectories are on average. Okay. And that's basically what a potential outcome framework says. Okay. The way we will do this is we will map this potential outcome framework to tensor representation. In particular, the way I'm thinking of a three-order tensor is there are countries is one axis, the measurement or days on which I'm measuring is another axis, and different intervention like low, moderate, and high are third axis. Okay. So putting it another way, if I look at a data point on this gray slice for a country, United States, on day T, what this means is that the death count on day T in USA under no intervention. If I move to the other slice while keeping the same country and same time, you say, well, it's the same country, same day, but now under different policy or different intervention, and so on. And ideally, what I want to know is that I want to know data in all of these slices completely, but in reality, I'm observing only small subset of them. Okay, and the whole goal in causal inference is to fill up, in some sense, this kind of tensor, because those are the counterfactual things. So, for example, in the United States, I might have observed only this, but I want to know this and this. Okay, let's make a step forward, and usually, let's see sort of how we can take the classical causal inference method and think of them as a now what I would call tensor completion view. So there's two things, right? Experimental, which is like randomized control trial, is a nice example of that, or observational study, the type of things we are trying to do, or is a beautiful work that has primarily the reason why I'm talking about this is synthetic control. So let's see how those two map to this tensor framework. Okay, so ignore bottom line for a second and look at the first one. So first one says that what we do in classical randomized control, such as what's done for vaccine right now, is that there are potentially three different options, maybe vaccine 1, vaccine 2, and a placebo. There's a large number of different patient types, young, old, men, women, people from different continent or whatnot. The different patient types. There's a whole population. From there, all patient types are given all three different interventions. So a fraction of them go here, fraction of them go here, fraction of them go here. So for the purpose of tensor representation, effectively, I'm observing data across each slice fully. And from there, what I do is that I take aggregate data in this slice, aggregate data in this size, and aggregate data in this side, and then compare those aggregate numbers. And based on that, decide which drug is best for the entire population, not a specific patient, but entire population. And maybe I come up with this as an answer. That is, no control is the best, which is kind of sad. Of course, it looks like the news has reported that Pfizer's thing has worked really well, or Pfizer and BioNTech. Now, this is how I would view classical randomized control trial as represented through lens of tensor. Okay. Now, a little bit more refined could be that, hey, I've got some patients. Okay, so let's say I've got a patient group which are young group, but I don't have enough patient in young people that I can split them three ways. So I can, for statistical accuracy, what I will have to do is I will have to either give young patients drug 1, drug 2, or control. And let's say I decide that all young patients only get drug 1. Then all the other patients in other group, let's say old patient get drug 2, and maybe a middle-aged patient get drug 3 or control. And again, from this, what ideally I would like to do is fill up these white spaces so that then I can do classical randomized control, saying that on aggregate, over entire population, whether it's drug 1, drug 2, or drug 3 is better. Or more precisely, in a personalized case, I would say, well, for young people, actually turns out blue drug is better. For maybe the old people, it turns out the green drug is better, and gray drug is better for the intermediate age. Okay, so this would at least in picture explains that if we wanted to do randomized control at a population level or at a personalized level, again, one way to achieve that is view this as a tensor and try to fill it up. And I'll make this more precise in a second. The specific observational study that we are looking at has this type of data pattern. So this is my day 0. Before that, every country has gone through no intervention. After day 0, some countries such as United States has gone through effectively no intervention. Some countries have gone through moderate, and some countries have gone through very severe restriction. Okay. From this, I'm asking the question, the original question that we posed, where I'm drawing the curves, 3 curves. What I'm saying is that, well, for each country, can we fill up these white boxes? So that then if I can go back to one specific country, let's say a country like this, and I can look at what happens to it under gray, what happens to under blue, under green, and those are the counterfactuals. Okay. So let me pause here, see if people have questions. Again, all I've done so far is just taken the data and put it visually, and I'm trying to visualize it as a tensor. And argument is whether you do classical experimental studies or observational studies as this, it's about completing tensor with specific observation pattern. Okay, so in short, one way to view causal inference question is we're simply doing estimating tensor under different sparsity or observation patterns. And it's this view that will enable us to do a bunch of things really nicely. Now, of course, if tensor is arbitrary and there's no structure within it, it's very hard to complete it. So the question is that what are the structural assumptions one makes that enables different pattern and so on. Okay. So in short, the key questions that are there are what modeling assumptions lead to what sparsity patterns to be recoverable. And as we do this, and now as we start thinking of causal inference problem with different units coming into play, time and intervention, problem has become necessarily large scale. Like traditionally, one assumes causal inference problem where one draws 5 different variable DAG and then tries to understand it. And that's one of the reasons why computation has naturally not entered the causal inference. But once now we start seeing this as a question of tensor with dimension scaling, naturally computation becomes essential, and statistical question or information question and computation question would start trading each other off. And more precisely, what is feasible and what is not feasible might depend on what sorts of observations you might have, which allows one to have a concrete intellectual dialogue that we could not have before. Again, I will sort of briefly spend a few minutes discussing that aspect. But as far as this talk is concerned, I'm primarily going to focus on talking about a simple tensor factor model, and then how that enables a specific type of sparsity pattern, in particular the pattern that we have been looking at using synthetic interventions. Okay, so this has been setting up, so to speak. Let me see if I lost folks here, if there are questions. Okay, no questions. All right, so in remaining time that I have, I primarily want to go through the algorithm. And so I'm going to go through it slowly, so please feel free to interrupt me at any point of time. So let's start with the question of tensor estimation. Okay. So really what we want to do is something like this, right? Again, I'm plotting here post-intervention. So let's say this is the time 0. This might be United States, this might be Turkey, and this might be India. And what I want to know is for United States, what would have happened if it had followed the suit of India or that type of restriction in first 15 days? That's a question I want to ask. Well, we haven't seen data for United States, but what if for some reason somebody told that the behavior of United States under these kind of different policy restriction would look exactly like how India behaved? Then one way to know what would happen to United States is to go to India, which has gone through this green policy restriction, and somehow extrapolate it. Okay, it's like saying that if for the purpose of the observation that we care about, US looks like India, then let's just, and India has gone through the green intervention, even though so US not gone through, let's just take India's data and sort of make it look like it. It's like they're similar. Okay. So the whole idea here is to somehow figure out similarity between different units and use that similarity. And that similarity we might determine not after intervention, but before intervention, and then use that to do appropriate extrapolation. Okay, and that's the basic conceptual idea to make everything feasible. Okay, and as I mentioned, the way we will compute similarity is potentially not after intervention, but pre-intervention, where all units were in the same situation. Everybody was normal, no mobility restrictions were there. So maybe we use observational data across different countries, which are nice time series, and then use some relationship between them. Okay. And that's basically what's happening. All right, so that as an intuition, let's start sort of looking at the precise algorithm. Now, as I will go through the algorithm, some of the notations I will use would look structurally like this. There's always a slice. Again, each slice, different color slices are for different interventions. There's always a day 0, before which there's some amount of time t0, where those are the number of measurements I have without any intervention. Or more precisely, during that time or during those measurements, all units were experiencing identical intervention. It could be no intervention, or in general, it could be any intervention, but all of them are same. Okay. And what we're trying to do in this situation is what happens to a specific unit of interest under a specific intervention or not. Now, what I would like to do is that I quickly step back there for a second and remind us of this really nice work on synthetic control. Came out of thesis of Alberto Abadi, who is my colleague here at MIT in economics, as well as member of IDSS. And I primarily learned this method from him, and at some level, I'm thankful to him for all the things I'm presenting here. Okay. So what is this really nice, simple insight that Alberto had? So he says, well, let's look at a very simple setting, a simple setting where there is one country, let's call it United States. On day 0, it went through one intervention. After day 0, however, every other country did not go through any intervention. Okay. And what I would like to know, what happened to US if it did not go through the intervention? I know what happened to it if it went through intervention, because that's what it did, but what if it did not? Okay. That's the type of question synthetic control tries to answer. Okay. And the way it answers is it focuses on only one unit, It expects all other units to do nothing, okay, and then somehow fill this one row, so to speak. Okay, so how does it do that? Well, it will first try to learn what I would call a model, that is similarity. So again, what is this data? So these are T0 is the time instances when we have observed data for all units. And this is simply the units which are donor, that is not the specific unit that we care about. So in some sense, we have, let's say if these are n units, then these are columns of length n. There are T0 columns, okay? And here, for simplicity, let's assume that this is one-dimensional data. Let's call that y. Okay, so I've got a vector of length T0, and this is a matrix of n by T0. And what we'll try to do is we'll try to learn a linear model between y and these n units. That is, a number here is a linear function of numbers in the first column and so on. And putting it simply, we are trying to do ordinary least squares here. Now, in general, synthetic control is not just ordinary least squares because it tries to keep a specific restriction on the linear combination learned. In particular, it will require that these W's or weights that we learn are non-negative and add up to 1. That is, that try to restrict the linear model to be a convex combination. Okay, with the intuition that, well, if the model turns out to be 0.2 here and 0.8 here, it will say that, well, USA is 20% like first country and 80% like second country. All right, so this is the model that we learn. Let's call it beta hat. Once we learn this model using pre-intervention data, we want to figure out what this is. We'll do this by using other countries' data post-intervention and the model and extrapolate. Okay. That is, we will say that m hat is the same z that we have here, but multiplied with beta, just like classical linear prediction. And that's it. All right, so it's a good place to pause for me and invite some questions.
If you're using another country's data, isn't it like transfer learning?
Absolutely. Thank you for saying that. So this is very much like transfer learning in a simple sense. And as we'll go through synthetic intervention, actually it is transferring learning not only across countries, or rather sort of, it's a model between countries, but it will truly transfer model learned in one intervention to other interventions. See, one nice thing that happens here is that we are retaining the model between countries under the same intervention, that is in this case gray. Okay, we are not using it for blue. So in that sense, it's a less of a transfer yet. But if we start transferring it model across intervention, that is even more transfer in that sense. And that's what will happen when we go to synthetic intervention. That's a great point.
Thank you.
Excuse me. I was wondering, like, so this Z-pre, supposing these are pretty small countries where the
Yes.
number of deaths are pretty small compared to Y. So the convex combination would not be ideal in that case, right? I mean, the magnitude of entries in Y would be much greater as the country size is bigger. So
Brilliant point. So, in a sense, my initial engagement with synthetic control was exactly on this this point, Symantec, right? Well, beautiful name, Symantec. Yes, so that's exactly the point. That is, you don't want to necessarily restrict yourself to convex combinations because magnitudes can be off, and there's no reason why, there's nothing so sacred about it. Convex combination, the reason Alberto and colleagues like it because it has certain, as they call it, regularization property. But one argument against that would be, well, let's just explicitly regularize it, okay? And that's basically what we'll do. So thank you for the question because it exactly sets it up for the next one. Now, before I move, did I miss any question from earlier slides? Okay. All right, so now we want to take the similar approach with a few modifications. One modification as Shyamantaka suggested, and one modification is the other gentleman suggested in the context of transfer learning. And from there, we want to arrive to synthetic intervention, okay? And so if you understood synthetic...
Devavrat, sorry, this other gentleman is Pushpak.
Okay. Hi, Pushpak. How are you?
Yeah, I taught you in IIT Bombay.
Of course, I know. I mean, this is where the not seeing in person is the difficult part.
Okay, thank you. Right.
Thanks, Pushpak. Yes, I should call you Professor or Sir, as we used to. So coming back to the going from synthetic control to synthetic intervention, method remains the same. Effectively, we are going to transfer things. We are going to transfer to do two things. One is not just do as we did in synthetic control, but we will also talk about different intervention. That is, not only we want to know for a given unit what happens if it continues with the same setup, but also with some other interventions across. And we don't want to focus on just one target unit. We want to go across units. Okay. And so that's basically where we are going. So how will we do that? Again, very similar thing. That is, there's a time zero. Before that, all countries are under same intervention. Say here, gray. We will learn the relationship between the unit of interest. So let's say I want to figure out what happens to the first unit under blue intervention. What I will do is that I will focus on the first unit and try to learn a linear model between this and the units that have received blue intervention after time zero. Okay. So that means that I'm going to try to learn linear model between Y and Z pre, but well, I will restrict to rows that corresponds to the unit that have received blue intervention after time zero. Previously, we went all over. Now I'm going to restrict myself to subset. And that subset is chosen based on who gets blue intervention after time zero. To learn this beta hat, what we'll do, as Shyamantaka suggested, we'll take this Z pre, and it's likely to be noisy as we discussed in the potential outcomes framework. It might be have lots of missing values too. So we will do the usual, let's say, the data processing. That is, we'll view this as a matrix. We will denoise it through one of the standard matrix estimation method. That in turn, and then after that, we will use that denoised matrix to learn the linear relationship. We will not restrict ourselves to convex combination or non-negative numbers. We'll just do the classical ordinary least squares. But because we have denoised things, in effect, it would have both effect of regularization of like a ridge regression, which is good for prediction. That is, it tries to restrain the two norm of your model. And it will also have sparsity inbuilt into it. In that sense, it will also try to keep the model sparse. So it has both L2, L1 regularization in that sense. You learn that model, and then to predict or estimate the counterfactual for the unit of interest under blue, take the same post-intervention data, denoised, and then apply your model that you learned. Okay. And that's how you get your post-intervention. Let me pause here. So again, it's a same method as effectively synthetic control, but as Professor Bhattacharya suggested, we are now doing actually a transfer learning, is going from model learn in gray environment to model to blue environment. And then we are restricting our model to only units for which we have observed things in blue, not everything else. And as Somantek suggested, let's not sort of keep it convex, but have it sort of general, but denoise the data. Okay, so this is the method. This is exactly the method that we used for producing all those curves. So let me sort of pause here and see if there are questions. Otherwise, I'll continue parsing the method a little bit further. Okay, if not, now just to sort of make sure that sort of I've communicated it precisely, let's say instead of blue, I wanted to do green. What I'll do is that now I'll restrict myself to donors who got green intervention, learn the model that. So this will be a different model, of course, because there are different units. And using that model, I will complete the green thing using this data. Again, this model that we learned beta hat is, of course, it's specific to unit that we want to complete, and it's specific to the donors we use to complete different interventions. Okay. And as I mentioned, we want to sort of denoise things, and when we denoise it, effectively leads to L2 L1 regularization, because we are effectively using principal component regression method behind the scenes. All right, and the question is that sort of why should this transferred learned model should work? I mean, we learned model in gray, why should it work in blue? So in synthetic control, we learned model in gray and we use model in gray, and hence there was no transferring happening, but here it's real serious transferring happening. So of course there has to be a structure, otherwise this won't work. And the structure that enables this is, in its simplest form, it's a tensor factor model. That is, this tensor of data that we want to complete, the average tensor that we want to complete is effectively has a low tensor rank in the classical sense. That is, it decomposes R components. There's a component associated with units of rank R, components with time, and components with intervention. Okay. Now, of course, this is exact. Both method and theory would naturally go through if you think of approximate version. More generally, if you have a generic factor model where value here is a function, some reasonable function, let's say a Lipschitz continuous function of low dimensional data associated with unit, or sort of latent factor associated with unit, factor associated with time, and factor associated with intervention, because for such functions effectively, or for such setting, you can argue easily that even though this seems like a nonlinear model, it can be well approximated by some linear or low rank structure. Okay, so in sense, for the purpose of this rest of the, let's say rest of the 5 minutes, you can think of the low rank structure. Once you have low rank structure, it's not too hard to argue that for any slice, the relationship, linear relationship between units remains invariant, because for any slice, it can be represented as U, some V transpose where V changes per slice, but U remains the same. And if U remains the same, the linear relationship between different units across rows would not change across slice. And that's why the model that we learned across slices remain the same. That's why I can learn the model in gray slice like this and transfer it to green slice. Okay, and that in a nutshell is the reason why synthetic intervention works. Of course, to get everything done properly and tidy up and make proper formal statement, you have to do the usual juggling, but this is the intuition. And now I can see that it's 6:52 my times, which means I'm minus 8 minutes from the formal conclusion of the talk. So I should pause here and invite questions. A bunch of things I might just briefly mention in a few more minutes that I will take, but let me pause here and see if I've communicated at least the method and the intuition why it works or when it should work. Okay. So this, in a sense, is just a proof that I gave a slide back. Okay, I think Manoj, you had a question.
Hello.
Yes.
Yes. So actually, I have a question to applying this method to something else. Like here you have some interventions in health. If we have like some different number of interventions to treat some disease, okay, like we have data for different interventions, and we have the result for results for each interventions. So what would happen if we apply the different interventions as compared to what have been applied on the set? So that it can be applied to.
So maybe if I understood your question correctly, what you are suggesting is that maybe let's take the classical clinical trial setting, right? And then try to understand what happens there, and can we reduce the amount of data required? Is that correct?
Yes, yes.
Yep. So, okay. So what I'm going to do is I'm going to sort of come to your question in a second. Let me just sort of do this 3-minute very fast forward of review slides, and then sort of come to that precise question. So again, so this is just to sort of explain that why synthetic intervention works, model transfer happens. This talks about a basic generative model under which, as causal inference world would like to call it, when can you actually do identification of causal parameter? Again, it's very causal inference specific take on this type of thing. All it says is that, when interventions are assigned to data, like countries like US got specific intervention because, hey, US has a specific type of a leader who is governing the country. And so there is actually relationship between the latent factors associated with the country that determine what intervention is received and what observations you see. And what it says that even in that case, as long as one assumes that subject to that characteristic of the country, once you condition on that, the assignment of intervention and the observation, the noise in the observation is independent, then it's okay. Okay. So even though we might have such a relationship through latent factor, it's okay as long as conditionally they're independent. Or they're completely independent like randomized control. Okay. There is because of this structural model, and there's a very nice clean hypothesis test that comes out. It's a very algebraic hypothesis test. It's also a test that allows you to start thinking about model generalization. So, and traditionally, when you are in supervised learning world, you say that you learn your model under some distribution, and in the same model, you try to understand how your error would look like. In our case, as correctly pointed out, we are doing transfer learning. So how does the generalization theory work? Again, similar simple algebraic property helps you argue how does one think of generalization. And so in a sense, this is kind of a generalization theory, I would like to say, which is very data dependent rather than the classical generalization theory, which is like Rademacher stuff where it's a model class dependent. And there's something nice and something subtle happening. I don't think I fully understand the proper implications of it, but I do believe that there are seeds of something interesting here, and some of the young minds out there might actually pick up on something like this. I'm going to skip all of this. There's a proper theorem you can get which says that the error that you will have would scale like 1 over T0, that is how many samples you have pre-intervention and how complex your model is, and how complex your rank of your pre-intervention data. Okay. And this is just a classical table comparison. I'm going to skip that. Here is one remark that I would like to make. That is, and I think this is something I'm the most excited about, is that once we map the causal inference problem as a tensor estimation problem, then actually there is a really nice discussion we can do, saying that what are the observation patterns that can be recovered in a computationally efficient manner. Now, tensor estimation as a problem has been nicely studied in machine learning, and usually the patterns people study there are randomly observed patterns. But here we studied this kind of a block pattern. Okay. In both cases, the sample complexity scales like n raised to 3 by 2 when you're tensor n by n to recover everything with in effect consistently. In both cases, you have polynomial time computation. In this case, there is a nice conditional hardness result known that says that less than this, there is no computationally efficient algorithm. So now the question is that, can we sort of start having a discussion about, are there other patterns that you can design? This also tells you that what are the experimental design you want to do. And again, I don't want you to think of this as kind of a race as you would run in computer science. It's more about design question and understanding rather than thinking of it as a race. Okay. Coming to the specific question Manoj asked, I'm going to sort of skip this study, but I'm going to talk about this one. So imagine you have a setting like this. You have 25 different user groups. You can think of 25 different types of patients, 3 different drugs and control. So there are 4 different drugs or 4 different interventions, and 8 days over which you are measuring. So you've got a tensor of 25 by 4 by 8. Okay. And if you do A/B testing like this, what you can do is for every group, for every drug, for every day, you can get data. And that's what we got, and hence that's the ground truth. Question is that to our method, can we show a small fraction of it and ask it to fill it up, right? And that would be nice, because now we can do randomized control without doing every experiment. And that's exactly, in a short answer, that's exactly what we did here. Again, I'm not going to dwell too much into detail, but R square turns out to be really nice, and we can here explicitly evaluate it because of the fact that we have all the observations available. So hopefully, Manoj, it gave you some answer to your question, maybe not exactly the question you were looking for. My time's up, so maybe I should sort of politely stop here and not talk about the connections to error and variable regression and all that. Okay, I'm just going to...
Okay, let's thank Devavrat for unmute yourself and clap to thank Devavrat. So maybe you can take a few more questions.
Thank you, everyone, for joining.
Any more questions? Okay, looks like everybody asked the questions they had during the talk itself. So thanks a lot for a beautiful talk. I wish, I hope to see the rest of it also someday. Not which you sort of rush through. So thanks again for accepting our invitations and giving this wonderful talk. I hope it kind of sets the tone. It's just the third talk in the series, so I hope these standards and sort of quality will be maintained throughout this series. Thanks again.
Well, again, thank you for inviting me. It's my pleasure. And hopefully I'll see you in person soon.
Thank you.
Bye.
Thanks, Devavrat.